Now we have seen about transfer function for first order. So that is for mercury thermometer. Now let us see various other examples for first order response. First one, liquid level system. Liquid level system. First order system, we have seen the example as mercury thermometer. Now we'll see liquid level system. Liquid level system is nothing but, consider a vessel where inlet flow rate is given as Qt, outlet flow rate Q0T, and it has certain resistance R. It has a certain resistance R. It has a certain resistance R. So there is a relation between the height of the tank filled and flow rate is given as Q0 is equal to H by R. A relation between volumetric flow rate and the height is given as Q0 is equal to H by R, where R is the resistance. Okay. This R may be resistance offered by a valve or any other pump, or it can be a pipe or any other thing. It can offer the opposite or resistance. Okay, resistance media can be through weir, valve or any other pipe. Okay, so now this is the relation for volumetric flow rate and head, which is known as H, height of the tank. Okay, now you will write, in this case you cannot write energy balance. Here you have to write mass because liquid level, so you are filling it out. So submit it in terms of weight. So you take mass balance equation here. So as it is, first step, mass balance in unsteady state. Mass balance in unsteady state. Mass is what? Density into volume, because you have volume here, which is Q. So density into, what is mass balance? Inlet minus outlet. So rho into Q of T minus rho into Q naught. Simply I will take Q of T and Q naught as Q and Q naught. I am easily, to avoid confusion, I am writing it like that. Okay, is equal to accumulation. Accumulation is what? D by dt, density into volume. Volume is what? Area into height. Because here what is accumulation? It is based on the area of the liquid level, right? So you cannot tell directly density into volume. Here volume is something, here you are leaving volume is something. So what is accumulated, we don't know. So that accumulated mass is density into volume, right? Volume can be written as density into volume. Volume can be written as area into height. Area into height is volume. So you can write density into area into height as mass. Right or wrong? So it is d by dt of rho AH. Rho AH. And density and area is constant. In this complete picture, density and area remains constant, height varies because you are adding some liquid and some amount leaving. Sometimes it will be certain height, sometimes it will be at lower height. So it varies. So height is a parameter which varies here. Density and area remains, density of the substance and the area of the tank remains constant. So this is what? Unsteady state. Now for steady state you write density Qs minus Q naught S is equal to d by dt of rho A into dHs by dt, which is generally 0. Generally 0. So now unsteady state minus steady state. Rho into rho, and anyway rho you can cancel on, you can take rho common here and rho common here. So throughout rho gets cancelled, right? If you take rho common, rho into Q minus Q naught, here also if you take, you can take rho common. So rho and rho on both sides will get cancelled. So remaining will be Q minus Qs minus Q naught minus Q naught S is equal to rho is equal to is equal to what? Rho is anyway cancelled. Area is there, right? A into d by dt of H minus Hs. H minus Hs. So 1 minus 2, taking rho common on both sides, rho will get cancelled, isn't it? Isn't it or not? So subtracting these two equations, q minus qs, q naught minus q naught s is equal to so and so. But we know q naught is h by r. So q naught of s will be at steady state hs by r. Yes or no? Q naught is h by r, q naught s will be hs by r. So this can be written as q minus qs minus h by r minus hs by r. Or simply 1 by r into h minus hs is equal to a into d of h minus hs by dt. Now again you have to consider deviation variable q minus qs, h is equal to h minus hs. So q minus 1 by r into h is equal to a dh by dt. Now applying Laplace transforms. Q of s minus 1 by r into h of s is equal to a into s into h of s minus h of 0. Differential equation Laplace transform. Here you are applying Laplace transform. Okay, and h of 0 is equal to what we have taken? H minus hs. Right? H is what? H minus hs. So h of 0 will be h naught minus hs, right? Initially in the tank, at time t is equal to 0, what is the height? The same will be at the steady state, right? Initial height and the steady state height, won't it be same? Because your calculations begins when the system reaches a steady state value. So your initial value and your steady state value will be same always. So h naught is equal to hs. Therefore it is 0. So h of 0 can be neglected, right? So therefore you have q of s is minus 1 by r into h of s is equal to a into s into h of s. As into h of s. Now taking r LCM, r into q of s minus h of s is equal to a into r into s into h of s. Taking r LCM, okay. Now take this h of s, that's other side. R into q of s is equal to ar s plus 1, ars plus 1, ars plus 1 into h of s. We'll take time constant tau is equal to ar. Time constant t is equal to ar. Let us take time constant tau is equal to ar. So tau s plus 1 into h of s is equal to r into q of s. So therefore q of s by h of s is equal to r by tau s plus 1. This is the relation between volume and the height of the tank. So your input is your height. Means you are filling it at a certain height. Your output is what? The flow rate. So at certain height, this is your flow rate. This will give you the relation between height and flow rate. Okay. So this is the derivation for the liquid-liquid system. Liquid-liquid system. Same as you have done for the previous. Instead of energy balance, you will take mass balance. So then inlet mass minus outlet mass is equal to mass accumulated. Same in steady state and steady state you will write. You will subtract. Again you will take deviation variables. Deviation variables after you take, then go for Laplace transform. You get the QS terms. When you expand that, you get Q of S is so and so. You get it. There again after that you will take h of 0 is equal to 0 because initially the height and the steady state height, initial height during when you begin the calculation and the height at steady state will be generally 0. I mean generally same, sorry. So h naught and hs will be equal to h. So h minus h will become equal to 0. So h of 0 will become 0. Therefore remaining when you simplify that, and you will take here tau is equal to AR. Tau is equal to AR and solve that. So this is your liquid level system. Now, second example. In the previous we have seen liquid level, right? Here also we will now see liquid level with constant outflow. Here liquid level with constant outflow. Liquid level with constant outflow we will see here. So in this case, with constant outflow will take. So liquid level with constant outflow. So same thing you will fill with a certain height. Inlet is Q, Q naught. Sorry, you are taking inlet as Q, right? Okay, you are taking inlet as Q and Q naught as the outlet. And here this flow rate outlet is kept constant. It is kept constant. It is kept constant, right? So again for unsteady state you will write the same equation. So in that case what you had, Q naught is having a relation is H by R. But here you don't have any relation because there is no resistance offered. There is no resistance offered. So your Q naught is kept constant. So unsteady state calculation is same thing. Q minus mass Q. So rho Q minus rho Q S. Sorry, rho Q naught inlet minus outlet is equal to accumulation. Rho into A into d H by dt. Rho AH density into volume. Volume is area into height. Right. And steady state case. Rho into Q minus rho into Q naught S. Sorry, Qs minus rho into Q naught S. But the fact is Q naught is kept constant. So your Q naught and Q naught S will be same. Q naught and Q naught S will be same. So Q naught S and Q naught will be the same because your outlet flow rate is kept constant. So Q naught and Q naught S will be same into dHs by dt. So this Q naught S can be written as Q naught because it is same, constant. So unsteady state minus steady state. So again 1 minus 2 rho into Q minus Qs minus rho into Q naught minus Q naught. It is 0. It is 0, which is equal to rho into d H minus Hs by dt. And rho on both sides gets cancelled. So capital Q is now again consider deviation variables. Capital Q is Q minus Qs. Capital H is H minus Hs. So therefore capital Q is equal to A into d capital H by dt. Now are you clear in there? There you got Q minus Qs minus Q naught of S. And there you had a relation of Q and height, which is H by R. But here there is no resistance offered. So your outflow is constant. So Q naught and Q naught at S will remain same. So this when you subtract it becomes 0. So here you only have 1. Q is equal to A into dH by dt. Now apply Laplace transform. Q of S is equal to A into S of H of S minus H of 0. Again H of 0 is 0. Why? Because the height at initial value and your steady state value will be the same, because when you start calculation your H and Hs will be same. So it is 0. So therefore Q of S is equal to AS into H of S. AS into H of S. So therefore here your relation is h of s by q of s is equal to 1 by s. H of s, there you got q of s by h of s as, there you got q of s by h of s, sorry, there also you got r, right, there also you got r on h of s, right, as r by 1 plus tau s plus 1. So your input flow rate will give you how much height it is filling. Clear? So this is liquid level with constant outflow. Now the last one, sorry, last second I mean, mixing process. These are all examples for first order. Mercury, liquid level with constant outflow. Now we will be seeing mixing process. Mixing process. Now this mixing process, what we'll consider is, we'll consider mixing of a salt. Mixing of salt, you will consider the volume to be constant in this case. Volume of the tank is constant. And here volumetric flow rate, it is entering at a flow rate Q, leaving at a flow rate Q. But its initial concentration is x of t, final concentration is y of t. Initial concentration x of t, final concentration y of t. So now we have to derive the relation between final and initial concentration. So we have to find out y of s by x of s, transfer function in this case. So again, it is concentration. Anyway, concentration also if you want to calculate, you are filling this tank, or mixing means you are filling this tank. So you are calculating mass. So again you have to go for mass balance only. So density, I mean flow rate into x, composition, concentration, component balance. How do you do? Q is meter cube per second. Meter cube per second. X is what? Concentration, moles per liter. So component balance, moles. Moles also is nothing but mass, right? If you multiply throughout with molecular weight, you get the same. You get it here in terms of moles per liter, right? Concentrations. So moles per liter, if you multiply it molecular weight, the total equation, will you not get mass? Right. That's what you are taking Q into X directly. Minus outlet Qy is equal to accumulation. This is an unsteady state, okay? Accumulation is what? V into volume. Volume into what? Flow rate of salt is equal to flow rate of inlet. Here also you write mass balance for component. That means inlet flow rate is equal to outlet flow rate. d by dt of Vy. Volume, meter cube, mole per second. Meter cube mole per second, meter cube mole per second is equal to meter cube moles per second. Clear? So anyway, volume is kept constant, dy by dt, qx minus qy. Okay, so unsteady state. Now steady state is qxs, qys, v into dys by dt, which is generally 0. So now again unsteady state minus steady state, q into x minus xs minus q into y minus ys, v into d of y minus ys by dt. Again deviation variables. So x minus xs is capital X. So q into capital X, q into capital Y, v into d capital Y by dt. Now take q common, x minus y is equal to v by q dy by dt. So volume, meter cube per second. Volume is meter cube. Flow rate Q, meter cube per second. So you get time, which is nothing but tau. So here V by Q will be taken as tau time. So x minus y is equal to tau dy by dt. Again applying Laplace transform, x of s minus y of s is equal to tau into s y of s minus y of 0. Y of 0 is y minus ys. Initially ys and y will be same. Initially y and ys at steady state and your initial value will be the same. This is our assumption everywhere. So y of 0 is 0. So this value will be 0. So x of s is equal to y of s into 1 plus tau s. So y of s by x of s is 1 by 1 plus tau s. Same that we got for the normal transfer function for mercury, the same you will get here. Okay. So here you will write flow rate and component balance you will do with respect to flow rate here. Okay, meter cube moles per second or meter cube moles per minute, whatever it is. So this is you have to go for flow rate, unsteady state, steady state. Subtract deviation variables, Laplace transform. This y of 0 is 0 because y minus ys at initial condition y and ys will be the same value. So it is 0. So y of s by x of s is 1 by 1 tau s plus 1. Next, last one example. Heating process. Heating process. So in case of heating process, you will write, obviously it is energy balance. So you have to take normally what you will do. In your homes, generally best example you use heaters, right? Heaters to boil water, bathing when you use heaters, electric heaters. Temperature Ti, W, T. This is the Q is the amount of heat that is passing through the electric heater. This is your electric heater. This is your amount of heat that is being given to the water or the fluid. Now, here you take the local temperature. At any point, take a local temperature.